This is section 10.3, Factorization of quadratic integers. Our goal here is to primarily observe how uniqueness clause in the fundamental theorem of arithmetic may fail. After that, a natural way to alter the theorem itself so that it is still true in a more general situation will be indicated. We start with some definitions, and the first definition is going to be quite technical. It's an integer d is called square free if c squared divides d, c, another integer, implies c is plus or minus 1. Basically, what we want to say, the integer is not divisible by squares, of integers, other, whatever. Or, besides 1, which of course divides any integer and is of course square of itself. So the integer is not divisible by non-trivial squares of integers. And since now on, we will assume for the rest of this section that integer d is square free. That will just simplify our consideration, which are the considerations are possible if we take this assumption off, but not so that is not going to be an interesting generalization. Things will look cleaner when we always assume that. Another definition, now not technical, but the definition of our central object of study. We call it z of d, of root of d, to be the set of a plus be root of d, with a and b just integers. That is a subset and actually a subring of the field of complex numbers. Or real numbers, reals sitting inside complex numbers if our integer d is positive. We actually can take it both positive and negative. Of course, I will write it. Oh, okay, I will not write it because the assumption that d is different from 0 is embedded into square 3. 0 is divisible by 4, which is a square. So when d is positive, this is a set of real numbers. When d is negative, this is a set of complex numbers. Some of them are still real when b is 0. And in either case, it is easy to check that this is not just a subset but a subring. So moreover, that is something I will not do, and you can easily do that. It's a very routine exercise, which, if it is not immediately obvious for you how to do that, then try to do that. If it is immediately obvious, don't waste your time. It is a very easy exercise that always this ring is an integral domain. So we have this is going to be running assumption everywhere, and we have a family of integral domains, one for every d. We'll study how fundamental theorem of arithmetic may or may not work in these integral domains. What is instrumental for our study is the presence of norm. So norm is a very helpful tool, very useful tool in the study of these rings. A definition of norm is simple, namely their function from our integral domain to integers given by norm of s plus t root of d. S and t are integers, is defined to be s plus t root of d times s minus t root of d, which is s squared minus dt squared, which is of course an integer because s, t, and d are all three are integers, and this function given by this formula is called norm. Clearly, when d was negative, the image of this function belongs to non-negative integers, while when d is positive, the image belongs to all integers. Norms may be positive or negative. I just stress that d may be positive or negative. We can consider for negative d a subring of the ring of complex numbers, while for positive d it is the ring of subring of the field of real numbers. So it may happen all positives, may happen both positives and negatives depending on the sign of d. However, it may be zero when both a and b are, both s and t are zeros, then this is zero. The following theorem is very easy to prove. In particular, it tells us that s equals t equals 0 is the only case when the norm is 0. So basic properties, very basic properties of norm. Are given in theorem 1019, which tells us, first of all, for an element of this ring under consideration, its norm is 0 if and only if the element is 0, meaning both s and t are zeros. And second, the norm is multiplicative. Norm of AB is equal to norm of A times norm of B for any elements A and B in our integral domain. Norm is a multiplicative function. Let me change slightly notations here. I will typically write S and T, not A and B, so let me change it in the first definition as well. I will write A and B for elements and of the ring, and typically S and T for the coefficients here for these two integers. Here A and B are elements of the ring, not just integers, and this A is an element of the ring. Element of the ring, I will write S plus T root of D. We already used norm for Gaussian integers. So if this is, let it be a remark to make things clearer, for Gaussian integers, the ring of Gaussian integers in these notations is z square root of -1, d equals -1, a square free integer. The norm n of s plus t root of -1 is, according to our formula, s squared minus -1, t squared means s squared plus t squared, makes it into a Euclidean domain. That is not the case in general. That is typically, well, just not. I don't know, I don't remember exceptions from the top of my head. That is not the case for arbitrary z root of t. So this is not only not a Euclidean domain, but frequently is not even a UFD. However, the norm is still of great help in the investigation of properties of these rings. For example, the presence of this norm function allows a neat characterization of units in a ring of quadratic integers. That is, subject of theorem 1020, U, an element of our ring, whatever D is a unit if and only if the norm of U is plus or minus 1. And the proof is very easy, coming from the multiplicativity of norm from 2 in theorem 1019 more or less after automatically. Look up the details in the book. From 1019 2 in the book. The characterization of units in this way allows one to obtain the ACC condition on principal ideals. Here is a proposition in our ring, our integral domain, the ring of quadratic integers, the ACC condition on principal ideals holds. This proposition allows us to conclude, as it was discussed in previous section, the existence clause in the fundamental theorem of arithmetic. So let me write it as a remark. The existence clause and the fundamental theorem of arithmetic follows from that as discussed in section 10.2. Thus, this proposition will allow for, not will, just allows immediately for an alternative proof of the existence clause. There is a direct proof of alternatively theorem 10.13 in the book provides another proof. Avoiding ACC. I think that it is more interesting to use the notion just introduced. So here is a proof of the proposition where have, so from theorem 1019 2, we have that norm of AB, whatever A and B are, is equal to norm of A times norm of B for any elements A and B from the ring. That implies that the absolute value of norm of product bigger or equal the absolute value of norm of any factor. In other words, one can reformulate that as A divides C implies the norm of C bigger or equal than the norm of A by absolute value. Let's now A1, A2, and so further be A3, be a chain, ascending chain of principal ideas. Ideals. Or what does it mean? The ideals are principal, and we can easily reformulate one ideal sits inside another one as a divisibility condition. So we have by lemma 10 19 1 that A2 divides A1, A3 divides A2, and so further. So every next one divides previous one. Now we take norms of all these generators of ideals. We considered only principal ideals. So let us take norms and recall that divisibility implies an inequality of absolute value of norms. Thus, we thus have n of A1 by absolute value is bigger or equal than n of A2 by absolute value bigger or equal n norm of A3 by absolute value, and so further. What do we have here is already a chain of non-negative integers, and non-zero, by the way, because if A is not zero, zero ideal is the smallest, not the biggest. So they are all not zeros, and at the same time the sequence is decreasing. Decreasing sequence of non-negative integers cannot be infinite. decreasing. Must stabilize. Other way to say that, look at the sequence of non-negative integers as simply as set. It must have its minimum element, and from this element on, all of these inequalities must become equalities. That was the minimum. You have to continue. Inequalities are no more acceptable. They are all equalities because you reached the minimum element. So what you have is, from some point on, you have that n norm of an is equal to norm of an plus 1 equal to norm of an plus 3, and so further. All of them must be equal by absolute value. At the same time, we still have divisibility, so an plus 1 divides an, as we had the divisibilities here. Every next one divides every previous one, every next one divides every preceding one in all sequence from point n also. That means an plus 1 equals c an, and we take norms. Norm of an plus 1 equals, norm is multiplicative, norm of c, norm of an. We can take absolute values everywhere, and these two norms are equal, an plus 1 and an. Implies norm of c is 1. That means norm of c itself is plus or minus 1. That means, according to just quoted theorem, let us look here. Where is the theorem we've just quoted? 1020. The element is a unit if and only if its norm is plus or minus 1. So C, we conclude that C is a unit, which by definition means that an and an plus 1 are associates. And That implies that an, the ideal is equal to the ideal generated by an plus 1. In fact, you can derive that immediately from the fact that C is a unit. You have this, and C is a unit. That's enough to conclude this. Similarly, an plus 1, the ideal is equal to the ideal an plus 2, and so further. We checked, we can conclude that the chain we started with stabilizes from some point on. This is exactly what ICC requires. Thus, the chain of ideals stabilizes from some point on, and therefore ascending chain condition on principal ideals holds for or in this ring, in the integral domain z of root of d. We thus proved that ascending chain condition holds, and therefore, as I mentioned immediately, the existence in the fundamental theorem of arithmetic is guaranteed in all these rings. So the rings are integral domain with ACC. Thus, we have existence. That finishes the less interesting part of our study of these integral domains, quadratic integers. More interesting, less routine part is about uniqueness, which may fail. Therefore, it is interesting. An example when the uniqueness fails to follow in the next fragment. Thank you for listening.